Now for the last talk of the day. Zoran Radovic is the senior principal engineer in the microelectronics division of Oracle. He's a graduate of Uppsala. He's working at Oracle in Stockholm, so it's easy to find him locally to ask a lot more questions about this, or if you're interested in the SPARC architecture. And he's going to talk about the latest SPARC. It's still SPARC, right? I'm saying this correctly?
Yes.
Mm-hmm. What is it? PowerPoint or PDF?
PowerPoint is fine.
Okay, here we are.
All right, can you hear me? This is working. So I have this unfair advantage of being the last speaker, the collective IQ, so I should have all the best answers and best architecture. I should have been here maybe 5 years ago, because these things really start a long time ago, right? As you all know, right? So actually using my title is called Software Hardware Complete. And this is something which popped up the day Oracle acquired Sun, actually back in 2010, all right, or something like that. And it was pretty obvious, the goal for us and the direction from the the founder and the executives at Oracle, right? So this is actually the first processor developed under Oracle's supervision and management, right? So this is an important slide I need to use. Many of these things could never happen, and we are really close to shipment date, so chances are really small that that's not going to happen. So just to give you a quick overview of the SPARC at Oracle, right? So if you haven't followed the high-end server business and enterprise computing, right, and mission-critical apps such as Oracle Database, so we've been shipping many of these processors in the last couple of years, actually. So when I moved to Silicon Valley back in 2006, SPARC T3 started. Actually, the same day when I just came to the first meeting, and all right, this is the PR, the plan of record. So since then, we have been doing the throughput multi-core, many-core computing for multiple years. So even before that, we had T1, T2, T2 plus, right, which kind of pioneered the multi-core space in the business. So so we started with the throughput cores. Over years, we learned how to make the single thread much better. So which Intel really pioneered a long time ago. So we're getting much better in the single thread performance, while many other companies are getting much better at multi-core. So we're kind of in a converging stage in this space. So and the SPARC M6 in this example is the really the high-end chip currently, right, in our kind of traditional big iron space. We can support huge memories, like 32 terabytes of DRAM in a single server, right? And you still preserve all of the traditional legacy virtualization, like hardware partitioning, which people used to have many years ago. So this is the strategy for my organization. So we are talking about extreme performance, computing efficiency, and really software optimizations for the Oracle software, right? And my job and my focus actually is really about this last point here, which is what can we do? What is really the value that we can add to these architectures, which is really unique for the company and for the customers. So one of the big advantages here, or the goals for us, is really we want to work together, right? We want to test and engineer the IP inside the company. And if you're coming from large companies, you often see that the deployment of technology actually goes much faster in case you have a control of all the different pieces of the stack, right, from the software, hardware, and so on. So, and that's in a way exciting for the engineers as well, because many people have bright ideas, right, and it's often much nicer to be able to deliver something much faster than waiting for many more years, right. As I said, this was actually the first processor managed by Oracle, and even the founder of the company was actually heavily involved from the day one of this process, right? So all of the tiny decisions we made and big directions were done together with Mr. Ellison. So Now we publicly announced this as a software in silicon processor in the recent Open World, which just happened a couple of weeks ago. So you might see this marketing aim coming up much more often in the future, right? So just quickly to give you the overview of the processor. As I said in the beginning, right, the first slide also of the strategy is the performance and computing efficiency, right? So before I jump to the all the unique software and silicon features which we have been developing, so I just want to give you a quick overview of all of the hard work which the entire organization needs to do, right, to be able to make a processor, right? It's a lot of work in the caching and the power management, I/O space. All of these things need to work together to make a product. So this is a 3-2-core chip, right? This is a fairly large, the biggest chip we ever made. So it has 8 dynamically threaded threads per core, so it's up to 256 threads per socket, right? The cache organization is brand new here. We have a shared level 2 data instruction cache. We have 64 megabytes of shared and partitioned level 3 cache, DDR4, up to 2 terabytes of memory per socket now. So these systems will go up to the 3.2 processors, which is 64 terabytes, which is really huge in memory database. So as I said, I will focus mostly on the application acceleration and coherent memory clusters, which are the new things which are coming in this processor, right? So the core was, we gave you an overview. I think D5 was presented at this conference maybe 2 years ago. So it's a similar core. It's fairly energy efficient core. It's also speculative core, same way what Intel was just presenting, right? So which is important for applications. We want to have ease of use, and we don't want to force special rewrites and coding, put the burden on the programmers. We have added a few new things in this core, which is the power management. We have the application, we have the line migration performance improvements, which are really important for virtualization when you want to migrate applications between different servers, so even in the same server, right? And the new things which are also impacting the core are the application data integrity feature, which I'm going to talk about more, much more about, and the few other things which we'll also touch on in the few slides here. So another thing which is important here, just to give you, kind of the background for this entire chip, right? So you get more information. We actually divide these in 4. We call it core clusters, which is really nothing to do with cluster computing, which I'm also going to talk about. So this is just the name for the on-chip divisions from the different units, right? So we have all of the 4 of these SPARC cores will be in the same core cluster. The new architecture, L2 architecture, was also heavily influenced by the applications which we support and sell, right? So we're looking at the database, we're looking at the Java applications, cloud applications which we are deploying, and by just looking at these in much more detail, we can actually tune for example, the iCache. Are we going to share the iCache, or are we going to have the separate caches and for different things? So this is kind of joint decision, right? Depending on the current state of the application space which we support, and also at the few years ahead of time, the roadmap in the software community, which we also follow, of course. All right, so if you go to the another thing which we can, if you look at these core clusters, as I said, we have 8 of them, right? 8 times 4 is 32. So we have eight of these clusters. Another thing which is also important, we need to be able to control the virtualization space. We need to control power, and this is maybe the answer to the discussion on the Intel presentation about the power array. From the architectural standpoint of view, we need to have all these hooks in these chips, right? So we actually can actually give you all the control to the Oracle Virtualization Manager or the OS. All these things need to work together, right? So actually to be able to sell these things to customers as a cloud solutions or any other solution you would like to provide, right? So the power management is described in slide. It's a fairly detailed story actually, but most of these things are moved to the die, right? As we also discussed before, adding control to the software adds overhead, right? And it adds, there's a delay how fast we can make certain decisions. So this is pretty on-die solution. It's pretty fast, it's responsive. It adds, we have 4 quadrants which we can control individually. So all this goes up to the higher level in the management software, of course. All right, another detailed slide before I jump on the new features is the L3 cache and the on-chip network slide. So this shows you the topology, how these units are talking to each other. A new thing which we're adding in this setup is are the accelerators for the database. So they're sitting closely to the memory controllers, and they can stream data, they can decompress things from memory, they can do certain database operations. So I will give you an overview on that as well. And the I/O and memory, of course, really important. Like I said, huge memories. So we have a long tradition of doing these big memory machines. So one of these first goals was performance, right? So these are the numbers which we are looking at today, right? So about 3 times over the thing we are selling today. So this should meet the performance requirement quite well. So we're pretty happy with that. So I should point out this actually doesn't include any new features, which might bump some of these numbers even more, hopefully. So. All right, so let's go back to the my favorite feature, which is number 1, application data integrity feature. Like I said, when we started this collaboration with Oracle, initially with the Oracle database, right? So I was fortunate enough to be one of the persons to attend all these meetings. So we started to have discussion. What do you want to have? What is the biggest issue you're facing in your day-to-day work or in the customer situation and things like that. So we started talking about things like memory corruptions. So as you probably know, Oracle database is one of the biggest and biggest parallel applications, right, available. So it's a really a huge number of engineers, and it was tested and deployed, and I think the record at some time was maybe 70 different architectures. So you can imagine number of testing, number of engineers working on this thing. It's a massive software, millions of lines of C code or C++ code, right? So if what we started to talk about is the certain corruptions which are happening, certain platforms which are really hard to nail down why they're happening, right? And of course, Oracle is a big software company, so they had engineers have been using all of these software tools, checker tools available, like Purify, Valgrind, or Parallel Inspector. However, if you start using these tools, and especially look at things like dangling pointers or silent memory corruptions, these are really hard to use, or they're really slow, right? Because the overhead for using them is maybe up to 100x, right? Which is really long, which is really big. Another big issue is the platform support, right? So as I said, the database is a huge application. Sometimes none of these tools work with these applications, right? In certain platforms, or so there's it's terribly difficult and time-consuming to use, right? Having said that, we use them all the time, right? But so we need to have something else. So so if you go back to the dangling pointer issue, if you look at that space a little bit more, so what really needs to be done here, what kind of Java language is solving, right? And these other new languages are that that you need to compare the pointer signature on every memory access, right? Which is basically every load and store. So if you start instrumenting loads and stores, it adds overhead, right? And the test coverage issues, right? How many cycles do you have internally before you ship a product? So you need to test these things for months and years. So your bug rates go down, of course, right? But the test coverage is still an issue, especially if you're using these slow tools, right? In addition to these tools, we of course need to develop much more tools and methodologies. So the multiple research groups and teams and who are assisting all the platform development. So the goal for us was actually really to have something in this machine, which is 256 threads, or even up to 32 sockets, which can be 8,000 threads, right, in production environment, which can track these pointers and help us with the issues we have, right? So that's the initial goal. So, all right, so a little bit more detail how this actually works. So this is really in production feature. It's a real-time integrity checking for test and production. So we can actually, the heap managers in the application can enable this, and they can version memory, right? As soon as you allocate a certain chunk of memory, you can put the version on it. So like in this slide, we have version, green version and a blue version. So for every load and store, right, every pointer which is getting, the heap manager will give out to the user or developer, they will also get the matching version. So the 7, it always needs to match 7, or if you hit outside that box, right, you will actually hit another buffer which is not your own buffer, right? And that's really what we call version miscompare, or you will get a signaling error back to the OS and back to the application. So we have this metadata which is stored throughout this entire architecture, right? L2 caches, L3 caches, all the interconnects, memory controller needs to deal with them, the scalability ASICs, basically throughout this entire machine. So we're shipping 64 bytes of cache line data together with this additional information, which is a tag for this additional version. So fairly intrusive. As you can imagine, I've been talking to many people to get this into this architecture, which is plenty of interesting conversations, and for me personally, in doing one of these big projects, was really a learning experience actually. But at the same time, it was really one of these things when you present an idea to somebody and people just get it and they just get passionate about it, right? So after a while, it was a big collaborative effort, right? So it was verification, and it's a huge amount of people who actually helped to pull this together, right? So if you go back to the open world just a few weeks ago, right? So we have Allison presenting this particular feature, and this is in the CEO or current CTO language, right? So what he would call it, he said security, security, security in the cloud, which actually wasn't, originally we discussed these things, right? The bugs in software, right, are really a common thing. Everybody knows about them, but then, bug-free software gives you secure software at the same time, right? In a way, we didn't really realize how important this is for the security, right? And I'm going to show you another demo here, or another example for the security application itself. So, like I said, this is hardware-based memory protection. It stops malicious applications from accessing other application memory. It was never been done before in the hardware space. And it greatly speeds software development. So I personally have been playing with this application or this feature myself, and actually, it's really amazing how quickly you detect your own faults when you start typing this code, right? Another slide from Larry. I think this says 21st century security. It's big words. So we really believe this is going to change the way we write platform software at Oracle, and hopefully many customers will have a chance to experience the same thing. Some media coverage is happening already, right? So we actually have a demo, and we had a demo a couple of weeks ago in Open World, where we can just link with the OpenSSL, buggy OpenSSL, which just triggered so much media coverage a couple of months ago, right? The Heartbleed bug. So this actually will attack the Heartbleed in production environment. like I said, Oracle database is probably one of the most tested software applications, and there's so much more software. We just want to make sure that all of that stuff is really protected as good as possible, right? So we go to feature number 2. So another really related thing, and I'm giving you the chronological overview of these features as we started to discuss the new architecture with different teams, right? So another really important problem, right? As soon as you have these bits in memory, right? We know from the research community, we're doing the garbage collection or any other kind of type of algorithms. It becomes really important and really hard actually to make certain algorithms to work without additional hardware support. So this is we can transform these bits to have another state, so we can kind of call them for fine-grained access control checks, right? Instead of doing the page control or MMU checks, which we do with the TLB, so we can kind of do the fine-grained check on the 64-byte granularity. So in this example, I'm showing you 2 different regions which have certain data marked for migration, and we can migrate all the data to another region, right? Which is a new clean piece of memory. So the good thing here is all of these instructions are fully user accessible. There's no we need to interact with the OS or any other special APIs, right? So, which kind of scales with the memory bandwidth, right? The memory bandwidth in your machine or the threads you have. So if you have 8,000 threads in a machine, it's going to scale with 8,000 threads, so that's fine. And also all of the conflict detection which is happening, I'm not going to go into too much detail about that, but these are really detailed architectural decisions, how you're going to trap on loads or stores, which information is getting back to the developer. We can control that as well, so we can give you precise information on a load or a store, or if you don't need that much precision, we can also control that. So it's always one of these runtime performance over decisions you need to have, right? So if you look at it, Java or JVMs, so the largest heaps we do today, right? As you know, right, Oracle is doing a lot of investment in Java applications. So we've been importing all of the business software to Java. So since maybe 7, 8 years now, we've been porting all of the business applications, and we're packaging in this new cloud solution, which was presented just a couple of weeks ago, right? So if you've been using Siebel, PeopleSoft, HR management, any of these applications, they will go to Java. They will go down to the JVM. And if you study these applications a little bit more, the heap sizes of these applications are really in the gigabyte range, right? They're not really in the terabyte space. Like I mentioned, this single socket can do 2 terabytes. And maybe the biggest Java application is, I don't know, 50 gigabytes or something like that. So we can put many of them on the same socket, right? So the heap sizes are much smaller than the 64-bit address space, right? And this gives us another advantage or another insight, actually, is we can enable all these upper unused bits today, right? As you know, Java is managing small objects. They're putting the object headers and all these other things on the heap. And they're doing all possible checks to squeeze up memory as much as they can, right? So we can actually control the behavior of addressing in this chip. So we can say, all right, I'll just use 40 bits for the JVM, and 24 is going to be kind of 3 bits, which developers can use, the JVM developers can use for the coding itself to make JVM faster, right? So a good example, if you look at the store barriers in the garbage collection again, you can actually, they have different barriers, different filters. If you do filtering in software, you know how filtering works. Normally you need to have some kind of table which you need to look up at runtime. And what is happening here is actually that we can certainly cache that state in the pointer itself. So when you go to the critical path in the application, instead of doing the indexing in a table or shifting these bits, we can just look at the bits itself and then make a decision on the fly. All right, so feature number 3 is database acceleration. So why isn't that the first feature? It's something I was starting to think about when I was sitting there. We actually, well, as I said, this happened chronologically, right? We started in-memory database in the software roadmap is slightly faster than the hardware roadmap, and these things are really difficult to match all the time, right? We have a five-year plan and a two-year plan. So, but we started to talk about in-memory databases quite heavily for a long time now, and this was one of these projects which were really interesting for me personally, because this is actually kind of a social experiment. What happens if you put the top architects in the database community with the hardware architects, and we have a slightly different language in the Oracle, as I've mentioned before, they supported Oracle on 70 platforms, so they definitely used to talk to hardware engineers. But in this case, they were actually forced to see the pain, all of the stuff happening in the background, right? When you have an idea, we have discussed something, then you actually need to be in the meeting and listen to the hardware discussions if this is possible to implement, if this is not possible. Normally what happens is that, they talk to certain companies, and these companies go away and come back with a solution. Or this is it. And in this case, this is a series of really long meetings, but really, really fun meetings. So I really enjoyed these meetings. So we probably talked over 2 or 3 years time period actually to come up with a few of these accelerators. And this is the slide I just took from this year's Open World, which was given by the database leads. This is maybe RFE for Microsoft. I just copied the slide for cut and paste from Oracle Red, just moved it in PowerPoint. Happened to be Microsoft Blue for some reason. I don't know why that happened. I don't know, some default color there. It's a default on the Mac. There we go. All right. I never figured out the templates. Anyway. So this is just one-on-one how databases are. What is the in-memory database? You've seen this, I'm sure, if you've seen this so many times before. But a big thing for the customers we have is real-time analytics, right? You have these customers like Walmart and big retails in the US, or in Sweden we have some other retails, but all of them are dealing with the real-time analytics these days, right? And actually putting stuff in memory speeds stuff up much more than anything else we have seen before, right? So we're using 100x here in this slide, but if you look at we publicly announced few examples, and some of these accelerations are in the range of 1,000 times, right? So from weeks to hours to minutes or something like that. Even seconds is really possible to do, right? So another thing for us is we want to mix this together with the OLTP, right? The traditional applications you have in a database. There's no need to change the application, like we discussed with the MPI and the OpenMP. This is really important, right? Because these are really big investments. On the customer side, you have a customer writing a big Oracle database application, and you just don't want to go to the customer and tell them, please rewrite this entire code to something new, which is going to be so much faster, maybe. So you just want to have this magical switch, which is happening right immediately. So this was a big software architectural change for the Oracle database organization, and they've been working really hard on this for many years now. So the row versus column format, right? This is the thing which is the key here. So traditionally, we've been doing the row format processing in the OLTP, right? So transactions run faster on row format, and in the analytics space, we all know the analytics runs on columns, so you can certainly much faster collect information if you have a tight loop over a column, right? How many people live in California or in Stockholm, right? That's what you do here. So, and then of course we can represent the columns in different types and formats. They can be bit vectors, they can be bytes or words, or they can be something else. Or so the Oracle software community, the big product release is called Oracle 12c. 12c, and the C is, I think it stands for cloud as well now. So we're doing, you can actually migrate the databases to the cloud versions of the database with a single kind of button. Migration button. All these products will support dual format, right? So you can actually, in the same application, you can support traditional application, and you can enable columnar application as well. All right. So if you go back to this chip itself, how does this map to the processors, right? So now it took us a while to understand what the plan of record is for databases, of course. I'm not the database software engineer, right? So initially, of course, all of these designs, and as we know, with any project, takes a while to kind of get stabilized, right? Now it's easy for me to come here and give you all the best answers, but but of course, these are long discussions, right? But we learned quite a bit how that works. And there's a team which is called the data layer team in the database organization, which deals with the data formats and how they put the data in memory and how they compress data. And so, what we've done here, actually, we've jointly developed a new compression format. So we can store data in the database with this new compressed format in memory, right? So all of the engines which you have on this chip, by the way, these engines are really tiny, right, compared to anything else. So they should kind of microscopically small engines. But they're custom silicon just for certain task-based operations. So these engines can decompress the information in memory. And these are vectors much bigger than any SIMD vectors. They can be megabyte large or gigabyte large vectors, right? And when we do the decompression, at the same time, the engine can actually make another function on this data, right? So you can decompress a bit vector, and you can find how many, you can count bits, or you can do certain range checks on values and things like that. So there's this fused operation which saves the bandwidth, right? There's no need to actually read the memory, put it in another buffer, decompress, put it in another buffer in memory, and perform operations on the fly there, right? So what we'll do it in a single pipe, so we can fuse the decompression and query functions. So we have 8 of these engines, and they're fully coherent, right? This is important to still enable they can operate on the entire memory space. So if you have 8 terabytes of memory in your server, you can touch all of these 8 terabytes coherently as any other processor core in the system, which is really makes this programming much easier than if we actually had some special engine which is using buffer memory or some other acceleration types, right? They can operate synchronously or asynchronously. So we have another user-level synchronization mechanism which works with these engines. And as I said, this is custom silicon, really high performance, which is peaking the memory bandwidth of the machine at really low power, right? And the real estate we're using for it.
These virtual addresses,
Right. So there's an API when you program the engine, so this translation is happening to the physical space. Yeah. But this goes through really quick path. So there's no real kind of system call, and there's a backdoor to the hypervisor. Just quickly on the synchronization, how this actually is implemented today. So what we have in this is something which also Intel is implementing in the privilege level, which is called load monitor and await instructions. So you can actually prepare an input for the engine. This is task levels. You say which function you're going to do. Actually, you create. We call it a CCB control block. You send that. Basically, you start this engine, and at the same time, you also send your completion area, right? So this is give me an answer when you're done. Store something here, and the application thread can go on and do something else, or you can just wait for maybe, I don't know, millisecond or something, or microsecond. Maybe millisecond is too big, microsecond is better. You just wait for 2 microseconds. Or you can kick off many of them at the same time, right? So this is fully up to the application, to the runtime, which is doing that. So important decision for us was really to make this application usable. It's one of these management questions you also have. Who's going to implement this stuff later? Is it going to be a database organization, or if I put it in a privilege mode or hyper-privileged? You basically directly control the implementation phase by making these decisions. So we didn't want to be limiting us by putting that in a certain level of the what is it called? Whatever is in, yeah. So anyhow, you get the point. So it's fully user visible, and we are certainly looking for other applications like general synchronization, right? Because this is a barrier. You can easily program that by OpenMP runtime management, the environment, for example. So some numbers from hot chips also. We see massive performance in decompression, I mean, compression in general is really difficult in software, as you know, and many of you know probably. And this is really the big value add for us. Actually, we can do the decompression much faster. A few other talks about decoherency. A few other slides. As you've seen before, in many of the processors we have been developing, like T5, for example, all of them are fully connected. So we pay the cost for coherency, and at the same time you get best possible scalability, right? So there's NUMA effects and all these other things are minimal in this environment. If you scale this up to even more threads, it becomes really large. So we have these sockets are grouped in four nodes or 4 socket nodes. This is still fully connected, right? The sizes of these, we can ship 5.2 terabytes per second here, which is a really large number. But also directly connected, right, which is really expensive solution, right, in this domain. So this is a picture engineering view of this thing. This actually goes all the way to 64 sockets, right? And we have 24 scalability ASICs. A lot of wires. Every single wire goes to all of the ASICs, right? And this is really kind of state-of-the-art big SMP machines. This doesn't get any better than this, right? So this is really difficult to build. At the same time, we are still going after the usability, right? It should be easy to use, easy to program. It's shared memory. You just use OpenMP. You just start 8,000 threads and off you go, right? At the same time, if any of these, if you're shipping cache lines here, so if just a single cache line dies somehow, right, we just lose that line, cache line, this entire box is going to panic, right? So there's so much stuff in this, and if you dig deeper into how people build these big servers, there's so many details, right, to protect every single transfer, and this is why this becomes so difficult to implement, right? But a single point of failure is really the argument for distributed software, right? And Oracle, and as you can imagine, this is a nice introduction slide to my next slide, why it is important with clustering. And in this case, what I mean is really real clustering in a sense. You have different servers, and which we need to handle. Complicated applications like Oracle database need to handle enormously good uptime, right? So if you buy tickets online or server dies, it's terrible if you wait for another 5 minutes or something like that. So we cannot handle that kind of stuff, right? So we need to have this redundant cluster in the backend, right? So traditionally, Oracle has a unique product called Oracle Rack, real application clusters, which is providing you a lot of that reliability, right, for the database application. So, in a sense, before I go into details of what you're trying to do in this coherent memory cluster mode of operation, so normally traditional Oracle deployment would have a really fault-tolerant storage unit, right? And the storage is kind of unified memory for all of the Oracle database clients. So if you start deploying Oracle on the Oracle Rack environment with maybe 4 servers, they will start caching this data from these big server nodes, right? And after a while, we can in the architecture, if one of these nodes just happens to die for some reason, it can be software reason or hardware failure or anything I mentioned before, right? The entire cluster will keep running, right? So this big fault-tolerant database or the storage is going to be there, which is fully replicating data. At the same time, we still have caching nodes alive, right? So it's important, right? One of these big things we I said, showed in the previous picture. If anything happens, anything goes wrong in this picture, right? We are dead. So this entire node is going to die. So going to the cluster environment, we just need to have this node that property, right? We need to be able to recover these really hard failures, right? So, like I mentioned, Oracle Rack has been running and being deployed in many cluster interconnects so far, like Ethernet or InfiniBand or anything like that, right? So, so with this new architecture, we also have another mode of operation, which we call coherent memory clusters. So even before I go into this picture, that's going to be complicated talk. So traditionally, all clustering, right, in the software is done with messaging. So we use scaling to many nodes, hundreds of nodes or thousands of nodes, right? But in the Oracle case, On the backend side, this number of nodes doesn't need to be extremely high, right? We go to maybe few nodes, 8 nodes or 16, up to 16 maybe nodes. But we're still using messaging, right? So there's a client-server model, and some of these algorithms happen to match quite good to the coherent SMP style of programming, but with the property that we just don't want to have this single point of failure property, right? So there's this disconnect. How can we create shared memory over the cluster? And we've seen this in the academia for quite a long time. I've been personally working on that for many years. Many other people in the audience, or a few people in the audience. But what is really unique in this Oracle setup here is that we can actually recover all these failures. So this actually is showing you an example of 3 servers. We have server node 0, 1, and 2, and each node owns a certain piece of memory, right? And then when you want to talk to somebody else in a cluster before that other node can talk to you, you need to have a handle of some kind of permission, right? So there's a handshaking mechanism. You can export your memory to somebody else. You can call that cacheable segment or non-cacheable segment. So there's this runtime environment which can actually enable you to open up windows to your own address space. And by doing that, we can go from the client-server environment to the client-only environment. So the client is doing the work. So if client needs to talk to somebody, he doesn't need to send a message, wake up this other node. He can just go ahead and read, use a store or read, right, directly to that space in some other server's memory. And I think I used in abstract of this talk, I used the word unbreakable, which is really a marketing word maybe, but actually what we have, and of course you can't really open up these windows widely to anybody else, right? Because they can overwrite and kill your server or something like that. So you need to give them a key, right? So what we do here is something similar to the standard interconnects. We have a secure access R key, which we share with these servers or nodes in a cluster. But we also provide another memory version, which I mentioned before, right? If you've seen this entire memory in our database is going to be versioned. So any data you're touching or you're working with, you have special version for it, right? So you actually need to give a version to these other servers as well, right? So there's this additional versioning which is going to happen. So it's much harder to actually break this cluster. A few more details about this. So we allow remote node, loads and stores and atomics. We have a little bit more relaxed ordering. All this is new software, right? So we're kind of starting from scratch a little bit. So we need to rewrite pieces of the Oracle database. Which is what you just mentioned in the last talk, right? Something you want to avoid. But in this case, we could push these programmers a little bit more. So you should add value to this product. So we need to have something more. And this is really, if you want to push the envelope, right? If you're going to change the way we communicate in the cloud, right? If you want to go from millisecond latencies to something like SMP latencies, there's no other way, right? We just need to change that. So, and this is kind of the opening door for that space, hopefully. This is showing the topology again of this cluster. So we're using fewer number of these. We are reusing the same scalability ASICs which we have in this massively scalable SMP. But in this case, the directories are turned off. We're just using them as the switches here, so we can ship. We can reliably deliver messages between these different CPU cores. All right, this is another engineering picture of this cluster. So we have 6 of these ASICs, self-redundant cluster or a switch, basically. From any processor core, there are 6 different paths, right? So if any of these link dies, we have redundant paths we can fail over on, and we can keep running for a long time before software really needs to know that something is going bad, right? So we have a chance of recovering and retraining some of these things. All right, the summary slide, going back to the goals, basically, this is a little bit of cheating, right? Because the presentation was written after the project was done, right? So we have the goals and then a summary, which is kind of matching exactly what the goals are. So we did improve the performance by 3x in this case, right? We've seen some of the virtualization enhancements. on the efficiency in the how do we manage memory and in the power management especially. And the stuff I was focusing on in this presentation is really the all of the new features for helping software getting much more reliable and to deliver new features in the software as well, right? Which is not only the hardware feature. So few of these things are actually running live, so you can sign up and test your application and see if you have any bugs, or you can also try using we're actually opening up all of these accelerators to external partners, right? If you want to write a new database or a new JVM, you're pretty welcome to do that. So if you just sign up there and you can try them out. So there's a full set of people which are going to support your efforts here. I think that was my last slide actually, so we can have a discussion on the features. Thank you.
Questions? Yeah.
Well, for the M7, you talk about application-specific hardware for different things. But do that means that you write specialized software but don't even compile for another hardware?
I'm not sure. Can you repeat that question?
Well, for M7, you
yes.
use special hardware for different things. But at least you may specify your software too much, or you don't really can go to next generation or another hardware.
Right. So that was one of these. I think this was touched on in the previous talks as well, right? This is one of these decisions as an architect. You need to make clever decision, and some of them are really hard. But we have much more experienced people in the organization than I am, so who have been around the block for a longer time. We've seen that before, right? So all this is heavily virtualized, right? So we can certainly fall back on any of these functions. I should say most of them. We're doing the best we can to actually fall back on the software-only solution, for example, right? If you don't have that feature on the next generation. But most of them are a part of the SPARC architecture itself, which is kind of the main document for any future chip designer we're going to have. So these features are fully supported for forever, basically, right? So we having these. Having these discussions. If you add one instruction, it's really hard to remove that instruction right later on. So, but you certainly need to compile a link with these new libraries, for example, right? So if you take the ADI as an example, that can be done fully transparently for most applications. I should say there, if you're really careful about really good C++ developer or C developer, you realize you need to be careful with certain things like pointer arithmetic, for example, if you're comparing pointers. So we could break some of these applications, right? But that's the trade-off you're doing here. It's really hard to make all of the legacy code work after so many years, right? So in some of these, we made decisions so that most of the people will get the benefit.
So you have eventually a 3x improvement in the evaluation that you did, but how much did you get out of every of these modifications that you did in hardware? So you show 5 different things that you did in hardware, and you get a 3x improvement. How much is one of them?
No, I think I mentioned that. Yeah. So that the numbers we are showing are done with the legacy code, with the current code, right? So that was. This is one of these big important decisions in the management school here. So obviously we delivered so many chips, right? And these people have learned the lesson. It's good to have people who've been working on failed projects. What I'm trying to say is important to focus on the baseline, right? In the new features are always, good to have features, but they shouldn't be kind of religious features. We need to deliver something. They're always a bonus, right? So we need to make sure that the baseline is really good, right? Before we add new things and maybe break something else, right? And then you don't have a product, so that'll be terrible. So another important thing here is really the collaboration with the software organizations, right? there's so many stories in the valley, right, where people design some really nice chips and then software is very late or they don't support your features, and that's not a good thing, right? So we're trying to make really joint decisions, right? So that the software organization and the hardware organization together deliver these features. So as I said, the numbers are not reflecting any of the accelerations so far, and that's something we will announce in a couple more months, I think.
You mentioned that you have energy estimation per core, and you could get this like on a quarter microsecond or something like that. Could you mention something what you use this for? So
first of all, having kind of reasonable energy consumption makes the engineering effort much easier for us. We can build these machines instead of kind of exploding instead of making them really unusable. So that's we need to package these things in a normal. There's a system organization, and they have certain limits, right? How much can be cool? What can be packaged together? So these are the regular things, and this gives us flexibility to control these constraints, right? Because it's also a moving target from time to time. But what I said in the presentation, like the virtualization, for example, right? You can certainly build a cloud solution where you can actually have a pricing model based on power consumption or how much performance you want to have, how much turbocharge do you want to have per your core or something like that. That's certainly doable, right? These are the mechanisms we want to build in, so we don't break the power budget or it's much more flexible for the consumer.
Any more questions? Can't see. About the accelerators.
Yes.
How are the accelerators themselves are virtualized? I mean, you have one per core, or how does that work? Or you have a bunch of them and then...
The bunch of them currently, it's also very flexible. So I think I said we have 8 of them, and then there's even each unit has multiple pipelines. So how we expose that to the software. I think each of the units is going to be single unit, right? So each pipeline is a CPU core, right? But that's something we can certainly change.
Right, but then the software needs to know that.
Right.
If it asks for a service, it might conflict with some other core that wants the same service, and how do you resolve this?
Right. There's this handshaking mechanism. You can actually there's a probe signal coming out from one of the accelerators coming, which is identifying exactly the thread which did the request, right? So we compare the request to the threads to keep the cache footprint, intact. So we didn't migrate to another. We didn't move the data. We can deposit the result to the same slice, for example, which triggered the acceleration point, basically. Yeah.
So you don't need to go through Solaris to access them. You can access them at user level.
Currently, there's a hypervisor actually, which is controlling this, but it's I think I mentioned that it's a really one of these really fast track accesses. So we bypass the kernel. I mean, there's of course the kernel and the hypervisor know about this acceleration, know about the memory mappings, so they talk to each other. Right? The application doesn't. Application talks to the OS, and under the cover, the OS is going to talk to the hypervisor in a really fast way.
So you're also shipping a new version of Solaris and a new version of...
Sorry?
You're shipping a new version of Solaris and everything, right, with this processor?
Yeah, of course. Yeah. We do that, yeah. So, yeah, that's required. And I shouldn't underestimate that effort. There's a lot of software work, and we haven't done that for a long time, so it's really, these features are not really, without a software community, that wouldn't happen, right? That's a lot of work.
Any last questions? Is there some? Okay, let's thank the speaker again. Thank you very much.